The first presentation is correlation between the mechanical behavior and the microstructural features of AISI 316L produced by selective laser sintering by Andrea, me, Piperopoulos, and Santonocito. Presented Dario Santonocito. Please, Dario. You have 8 minutes.
Thank you, Mr. Chairman. Good afternoon. And today I will present you a comparison between the mechanical behavior of traditional and additive manufactured steel, stainless steel. And in our work, we evaluate also the mechanical properties of the materials under static fraction test. And both we apply the infrared thermography to assess, according to the thermographic method, the first damage initiation within the material. So we make a comparison with an as-built additive manufactured material, because additive manufacturing nowadays it is adopted to make a final product, final part. So we want to assess the mechanical properties of such materials as built in order to make a final product in a rapid way. According to the thermographic method, the classical Risitano thermographic method, we can apply infrared thermography to assess the okay. So thanks to the Risitano thermographic method, we can evaluate in a rapid way the fatigue behavior of material. Un audio di ritorno. C'è qualcuno che ha il microfono aperto? Thank you. Sorry for the inconvenience. So, according to the Risitano thermographic method, we can assess in a rapid way the fatigue behavior of engineering materials, both metals and polymers, in a rapid way by measuring the thermal trend of the specimens stressed above its fatigue limits. So we can, in a rapid way, obtain information on its fatigue limit and on the overall SN curve. A new infrared thermography application is the adoption of the static thermographic method, according to which during a static tensile test, we have 3 different phases on the temperature trend. The first phase with a linear decrement of the temperature according to the thermoelastic law of Lord Kelvin. Then the temperature deviates from the linearity in a second phase. And finally, in a third phase, we reach the an overall macroplasticization state and until the failure of the specimens. So if we are able to assess the transition between the first phase and the second phase, so we can correlate this macroscopic stress with a damage stress that introduces in the material the first microplasticization. So in our work, we tested 2 kinds of materials, the traditional stainless steel and the additive manufactured stainless steel, and we with the same specimen geometry, and we adopted a servo-hydraulic load machine, and we also applied the temperature monitor with an infrared camera. For the selective laser melting steel, we adopted a laser power of 230 watts and a laser scanning velocity of 1040 millimeters per second. The specimens was built along the Z direction, and the static tensile tests were performed under stress controls. We also perform failure analysis, conducting metallographic inspection and SIM inspection. So here I show you the results of this static tensile test. As we can see, we have the linear decrement of the temperature, then the temperature deviates from the linearity. So we can make the linear regression of the temperature point of the phase 1 and the temperature point of phase 2 and make their intersection. So we can read a value of the limit stress. Here we report also the other static tensile tests performed on the same steel. And here I report the tensile test performed on the additive manufactured steel. So we can see how the limit stress is considerably low compared to the traditional material. In this table, I report the ultimate tensile strength and the average limit stress of the materials. So moving to the failure analysis of the material, we can see how the chemical composition analyzed by XRF is the same. It's the same for the additive manufactured material and the traditional materials. And performing the metallographic inspection, we can see in the left side how the additive manufactured materials has macroscopic defects compared to the traditional counterparts. By analyzing the microstructures, we can see how the traditional specimens exhibit a classical austenitic composition, while the additive manufactured specimen tested with the same etching procedure did not show any particular microstructures. So by analyzing the fracture surface with the SIM, we can see how the additive manufactured material exhibit a brittle fracture surface under static tensile load and several macro defects as unmetal powder. On the other hand, the traditional material exhibit a very ductile fracture surface with a small defect compared to the traditional, to the additive manufactured one. So in conclusion, as we have seen, we have a premature failure of the additive manufactured specimen with a lower ultimate stress compared to the traditional material. We also exhibit a very brittle fracture surface, and this may be addressed to the specimen building orientation and microstructures. And we also assess how, with the static thermographic method, we can obtain usable information about the damage initiation in the specimens with a very rapid static tensile test. Thank you for your attention.